For today's math lesson, we're going to continue talking about special kinds of triangles. We've talked about right triangles already. We've talked about isosceles triangles. And today we're going to be talking about equilateral triangles as our third type of special triangle. And we talked about equilateral triangles when we were beginning our unit of study on triangles. And we learned that equilateral triangles have all three sides having the same length. So for example, if this was a 4 over here, this would also be a 4, and this down here would also be a 4. So all of these sides are the same. Now, yesterday, when we were talking about isosceles triangles, we were also talking about how angles are formed, and we used the trick with the rubber band to illustrate how an angle, when it widens, makes that side length even larger or longer, and then when that angle is smaller and has fewer degrees, that side length across from it that closes off the angle is going to be shorter. So, keeping that in mind, if all three sides have the exact same length, then we can also deduce that all three angles are going to have the same measurement. The number of degrees in them is equal and does not change. So therefore, we need to consider what the measurement is in each of these angles in an equilateral triangle. Now, if there are three equal angles in an equilateral triangle, we need to figure out how many degrees are actually in here. So if we think about, there's 180 degrees in any triangle, not just an equilateral triangle, and then if I divide that by three angles to get how many degrees are in there equally, 3 can divide 18 tens 6 tens times. So I have that 6 up there. I'll subtract 18. I'll have nothing left over. I'll bring down that 0 so that 3 can divide 0, 1, 0 times. And then I can finish off and do that 0 subtraction, but I don't need to. So in an equilateral triangle, every angle measures 60 degrees. So this angle is 60 degrees. This angle is 60 degrees. And this one up here is also 60 degrees. Some mathematicians may also say that an equilateral triangle is also equiangular, meaning that all of the angles are also equal in an equilateral triangle. So to put this into practice, let's take a look at a couple example problems. And I'm going to try to move the glare around just to hide everything here. So here on this first example, we see that I have three sides that are congruent. So I can deduce that this is an equilateral triangle because I have three congruent sides. Now what I need to do is find the measure of angle x. So the measure of angle x is going to be given to me by realizing, hey, I need to figure out that there's three equal angles here. And again, that 180 divided by 3 is 60 degrees. And once we've remembered that there are 60 degrees in every angle of an equilateral triangle, I really don't have to do this division work anymore. The answer will never change on me. So the measure of angle x is 60 degrees. Now down here, we have angle y in our red ink. So we need to figure out, angle y is hidden by a glare right now. We need to figure out what angle y is up here. And the issue here is that we don't know if this is equilateral or not. We know that it's isosceles. Okay, we have two equal sides, which means we have two equal angles. So angle y is being pointed to by this equal side, and this side is being pointed to by this angle over here. So angle y and this other angle are equal. So now to confirm that this is actually an equilateral triangle, I need to do a little bit of math here. So I have 180 minus 60 degrees because this is the odd angle out. So that's 120 degrees. And then 120 degrees, remember the rule for isosceles triangles, we take our remaining degrees, divide by 2 to figure out what one angle is here. So 2 can divide 120 60 times. I'm combining a step there to save some space. So this is 60 degrees, and this is 60 degrees. All three angles are equal to 60 degrees. So guess what? This is an equilateral triangle. And this problem asked you to prove that this was an equilateral triangle. So congratulations, you've just proven that a triangle is completely equal on all three sides and in all three angles. What we'll take a look at right now is this next triangle. Hopefully the glare, yes, right there in the middle. All right, so ABC is equilateral. So ABC, so this side is equal to this side is equal to that side down at the bottom. Okay? Now, we have to take a look at a couple of different things here. We have to find the measure of angle DAB, so where this green arc is, and the measure of angle ADE, so where I'm going to draw in this red arc right here. And I'm going to move this over so that we can put that glare in the middle so that it's a little bit easier to look at. And now I have the measure of angle DAB. And, ooh, this problem is missing one critical piece of information. That's supposed to be drawn in there. So that critical piece of information is a right angle box. So right here, angle D is a right angle. Now, or right here by point D, there's a right angle on this line. So what I have to think about right now is there's quite a few triangles drawn on this paper for me, or drawn on this board for me, I should say. And I have a right triangle right here. I have a right triangle here. I have another one over here. And then I have this equilateral triangle all on the outside. So that means, and I'm going to take my black marker over here to draw in these angle arcs, this arc right here is equal to this whole angle up here, which is equal to this whole angle over here. So all three of those equal 60 degrees because it's an equilateral triangle. So if this is 60, this is 60, this whole angle arc, okay, is 60. Notice I didn't write the 60 over here by this smaller angle arc, which is referring to part of this angle. Now what I can do is I can use right angle rules to help me find angle DAB, this part right here. So I know that if I have a right angle, I only have to worry about 90 degrees and then subtracting 60 degrees from it. That 90 degrees is not the right angle. That 90 degrees is how many degrees are left in the triangle after I get rid of that right angle in my math. So I did 90 degrees minus 60 degrees, and I'm going to see that this is 30 degrees up here. So if this part of the angle arc up here is 30 degrees, I can also figure out that this part of the angle arc should be 30 degrees. And the reason for that is the whole angle up here by angle A, we'll call it angle EAB. Angle EAB is completely worth 60 degrees. Angle DAB is part of it. So part of angle A there is 30 degrees. The other part is what's missing over here. So that part is also 30 degrees. And that makes sense, right? 30 plus 30 equals 60. So we figured out that DAB is 30 degrees. Now we have this other angle that we use to help us is 30 degrees as we find ADE, which is this red arc I've drawn down here for us. So can I figure out what that is? Absolutely. Because here I can now trace this triangle right here. And once again, I see that I have a right angle. So this is a right triangle that I've just dotted out for us. And up top is a 30-degree angle. So I have 90 minus 30 degrees, and I'll be left with 60 degrees here in angle D. Now, bonus question off of this problem. Can I figure out what this angle is right here, angle EDC? You bet. And there's two ways I can figure this out. One of them uses the rules for triangles, and one of them uses the rules for angles on a line. So there's a couple different strategies that I can use to help me. In fact, there's two methods for angles within triangles to help me out. We'll focus on just one. So right here, I can think that this is a 90-degree angle and 60 degrees, so 90 minus 60 will give me 30 here. And if I imagine that point D has angles on a line, I have 90 plus 60, that's 150. 180 minus 150, this is 30 degrees in here. I wonder if there's another way that you could figure out how this angle comes out to measure 30 degrees. You might be able to use a different triangle on this to help. You can shoot me an email and see what your thoughts are on that one. Finally, we have one final example here, and we need to find the measure of the blue arc up here. Now, this might look like a parallelogram, and don't worry, we're going to get into parallelograms next week or later on, and we're going to take a look at the triangles inside. We see that there are one congruency tick mark on these three sides, so this is an equilateral triangle. On this triangle, however, there are one congruency mark on this bottom part here, and then I have two congruency marks on these sides over here. So that means that those two sides are equal, and this one is not. Therefore, this is isosceles up here, and this one is equilateral. So I'm playing with two triangles that are joined together. By the way, this wouldn't be a parallelogram. So in this particular example, we need to think about using some different rules to help us out. Now I'm going to grab an index card from over here so I can block out this part of the triangle for now. And right now I want to focus on this equilateral piece, because that equilateral piece is so quick and easy to work with. I see three equal sides. I should be able to recognize three equal angles right away. Okay, that part is done. That's the easy work. Now, let's get rid of the equilateral triangle and go to the isosceles triangle. So up here, I have two equal sides. Those equal sides are pointing to this angle right here and this angle right here. So this 30-degree angle is the odd angle in this isosceles triangle. So I have to get rid of it. 180 minus 30 degrees is going to leave me with 150 degrees. Then, because it's an isosceles triangle, remember I'm going to do 150 degrees, divide that by two equal angles, and I'm going to have 10 ones. So now I'm going to have 75 degrees in each of these equal angles. Now that I've found all the angles inside here, I need to now figure out the blue arc, because the question here was to find the blue arc. Realistically, they might tell you to find angle A, B, E, or whatever the situation might be. So we're just calling it the blue arc for right now. What is the measure of the blue arc? Well, if I have a 60-degree angle here, a 75-degree angle here, I'm going to put it together and be able to solve for that missing angle. So 60 plus 75, that's 135 degrees. And that will be my missing angle. So that's the blue arc right there. All right, so for right now, we're going to let you guys get started up on your Google form for today. So check out those problems, read everything really carefully. Reach out if you have any questions.